Welcome to the first lecture. In this lecture, we will see and review the classical information. We will start with what are bits and try to see what are single bit logic gates, 2-bit logic gates, Boolean algebra, reversible and irreversible gates. So let's start with bits. So we all are quite familiar with what bits are. We use them to store information. As an analogy, we will see a coin. It has two sides, heads and tails. The heads can be said as 0 and the tails can be said as 1. This can be used to store information. For example, if we toss a coin and we get heads, we know that we store the information as 0. Similarly, we can use multiple coins to store multiple bits of information. So if we use two coins, we can get head tails, tail heads, or tail tails. So we have 4 bits of information, and we can continue so on and so forth. So 3 coins, we have 8 outcomes, and when we have n coins, we will have 2 to the power n outcomes. So this is what a bit is. Now we have stored our information, but we also need to do something with our information. We need to access it or manipulate it, for which we use logic gates. So a logic gate is very simple. We take an input. Let's say if we consider this particular case, we take an input, say 0 0, and we'll apply a gate which will transform it to, let's say, 1 1. This is all what a gate does, and we represent the gate in form of truth tables. So the truth tables is a map from the input to the outputs of the logic gate. And this is the truth table is very helpful to look up what the gate does for a particular input instead of trying to figure out from the past. Now we will see some single bit logic gates. Single bit logic gate means a gate that acts only a single bit. So we are only considering one single bit, so 0 or 1. That is, we are only seeing one coin. The first gate is the identity gate, which does nothing to it. So 0 remains 0, 1 remains 1. The second gate is the NOT gate. The second gate is the NOT gate, which reverses the bit. So if we start with 0, we get 1. If we input 1, we get 0. Next gate is the always 0. So regardless of your input, the output will always be 0. The last gate we'll see for single bit is the always 1 gate. So we start, regardless of what the input is, we will always get 1. These were the single bit gates. Now see here that how many gates did we get? So we had two possible states. That is 0 and 1, right? And we got 4 gates for it. So we can say 2 to the power 2 square gates. Okay. Now let's see 2-bit gates. So 2-bit gates is exactly like 1-bit gate, but now instead we are dealing with 2 bits. So let's say we are dealing with 2 coins. This is coin number 1 and this is coin number 2, and each of them can be head, tails, head, or tails, right? Okay, so we have 4 possible states as we discussed here. These are the 4 possible states. These are the 4 possible states. I won't go into the details of these gates. I hope you are already familiar with the gates. This is the AND gate, the OR gate, the NOR gate. Sorry, this is the NAND gate, the NOR gate, and the exclusive OR gate. Okay. Now we will see multiple gates. So until now, what we have seen is we took a single input. We had a single gate here. and then we had an output. But what if we have to do multiple manipulations on a bit? So it would look like input, let's say we apply some gate 1, we apply another gate 2, and then we obtain our output. This is the purpose of multiple gates. So we can combine any number of logic gates to create more interesting operations. For example, we have shown here, we have combined two AND gates, and we start with 3 bits A, B, C, and we obtain AND of all these bits, and here is the truth table. So what it basically does is it only shows a positive or an outcome 1 when all of the 3 inputs are 1. Even if one of them is 0, the output is 0. This is a more complicated gate which contains an exclusive OR. So this is the exclusive OR gate, the NOT gate, and the AND gate. And you can look at the truth table and see what it does. Now, this gate is quite complex. However, this can be simplified to this gate, because why not? Who wants a difficult gate to look at? So we can simplify it. Now, how is this simplification done? It is done using Boolean algebra. I hope you are also familiar with the Boolean algebra. And here I just cover very briefly some operations and identities. So this is the order of the operations. If we have A plus BC, we will first do the AND operation. So this is the AND operation, and then do the OR operation. Associativity, these are quite trivial from your mathematics as well. Commutativity and distributivity. Now here are some identities for Boolean algebra. So this is A and 0. I hope you remember the symbol. This stands for AND. So here we have A0, so A and 0, which will always be 0, because remember the truth table for AND here, and we already have a 0 here, so we can never get 1, so therefore this is 0. Similarly, we can follow the other identities. So these identities was for when we are dealing with a single bit. There are 2 bits here, but we are just dealing with A, which is storing just one information at one point of time. Now here are some important 2-variable identities, which is A plus AB is equals to A plus A naught B is equals to A plus B. You got proof given in this line if you want to satisfy yourself further. These are the 2 most important properties, the De Morgan laws, and you will use them again and again and again in classical information. You can prove these yourself following the above rules, and it's quite trivial. Now we will look at another very important concept, that is reversible and irreversible gates. So let's consider this NOT gate. This is the NOT gate. So if we get 0, if we input 0, so if we input 0, we get output as 1, and if we input 1, we get output 0. So you see the outputs are unique here, right? And let's see this AND gate. We can clearly see the outputs are not unique. Consider you are a teacher and you have 3 kids, okay? And you give one of the kids a banana, one of the kids an orange. Let's name the kids PQR, and the third kid, an apple. Now let's say the kids are a little naughty, and after eating their fruits, they do not throw the remains in the dustbin. Instead, they spread them on the floor. Now you will be able to easily track, if you found a banana peel, you will easily be able to track that P threw it on the ground instead of the trash can. However, if you gave, let's say, banana to both P and Q and an apple to R, and now if you find a banana peel on the floor, you won't be able to tell if it was P or Q. This is exactly the situation we are discussing in terms of gates. So when we have two unique outputs, we can trace back the inputs. However, if we have similar outputs, for example here 0 0 0, you cannot trace back the inputs because you don't know which of the three inputs led to that particular output. So this was like, these were like really simple gates. Here are some more complex 2-bit gates. So example, this is a reversible gate. Why? All the outputs are unique. 0 1 1 0 1 1 0 0. None of this repeats. However, this is irreversible. Why? Because these two gates repeat. Why is this discussion important here? Because quantum gates have to be reversible. So, how do you make the gates reversible? You simply exclusive OR the outputs with a third bit. Let's see how this works. For example, if you have 0 0 and 0 0, these are the uh, information or the output that is being repeated. You take a third bit C and do an exclusive OR with that. Okay, so the C has two possible states, 0 and 1, and you map the outputs here. 0 0 0 0 exclusive OR will be 0 and this would be 1. I think it might be beneficial to review the exclusive OR truth table here. So we get an output if either this or this is true, right? So this is how it functions. So like to summarize, if any output is being repeated, we take an exclusive OR with a third bit, which gives us two states in return. Let's look at an example. The Toffoli gate. Toffoli gate is a really important gate in quantum computing, and you will see it again and again. Here we make the AND reversible. So we saw that here, that AND, this is the AND gate, it is irreversible, right? And so we'll try to make this reversible. So this is our AND gate here, and we exclusive OR it with a third bit C, and we obtain the following truth table. So let's try to map what was the original AND gate. So we have 0 0 0 1 1 0 and 1 1, and if you see the outputs of these, we will exclusive OR it with a third bit C, which produces two outcomes for each of these. So you now see all these become unique. So if we see this as a whole, 0 0 0 0 0 1 0 1 0, this, all of these 8 states are unique. And now we can map it back to check what our input was. So this is how we make a gate reversible. For this particular input 0 0, we had similar outputs, right? And at this point we exclusive OR it with a third bit C, and we obtain two different outputs, and this process repeats for everyone. Okay, so this is the end of our lecture. Now I have some exercises for you to try. You can take a screenshot or pause the video, whatever you prefer. So here you have to simplify the circuit using Boolean algebra and then also make a truth table. And this is related to the problem of reversible and irreversible gates. Okay. So thank you for watching, and if you have any questions, you can contact me by in office hours.